And now that the system is working again, we will the pleasure to hear the presentation of Alin on leg locomotion and the recent work he is doing in his RC project.
Yes, so thank you. I hope it's worthwhile, all this effort. I'm back with my computer. And I will talk about a geometric perspective to nonlinear oscillations with application to locomotion. And yeah, I focused on this project, which is on my current ERC project, because it was very much inspired by the work Jean-Paul has done. He has an ERC project also on geometry and locomotion. And we all know his presentations. He was a great scientist, but also a great presenter, right? Being able to conceive in a very intuitive way the things he has done. And his main idea is about studying the geometry of motion, but also, principles of efficiency and in human and robot locomotion. And you see here the Poincaré map, a tool for searching for periodic gates. So there's a very strong link and actually a direct link of inspiration to what I have done and what is my ERC project about. I'm looking also at locomotion, but from an additional perspective of studying oscillations. Probably my big part of my research career was linked to oscillations. I started fighting them for maybe 1 or 2 decades with Alessandro De Luca and others, and then I came to the point of loving them and trying to use them nowadays. And of course, the motivation is that biology exploits elasticity in order to excite nonlinear oscillations, but still in robotics, I think we do not have the right mathematics to do so. So I started an ERC project, well, because I'm at the German Aerospace Center. The motivation was about space exploration, but actually the main and deep motivation is really understanding the dynamics behind and how it can be exploited to understand biology and to improve locomotion. So from biomechanics, of course, we know those pictures about the cost of transport of animals, and all robotics groups are trying to pinpoint their performance, and we know that still general robots are below in terms of performance than biology. And one reason for that is probably that in biology, animals go into resonance modes for different gates. And the biomechanical experiments show that, for example, horses switch between different gates depending on the speed to get into resonance. And so every gate has the speed where it's most efficient. And then there's a very inspiring work by David Remy and his group showing that if you take a model, this is a very simplified model with massless legs and so on, but you take a passive model, give it the right initial conditions, and then most of the gates known for horses will emerge automatically. So they are embedded in the dynamics of the system. There's no control in here, just the right initial conditions. This is found numerically, and well, I think I still have to stop for a second because it's going into automatic switching, and I don't like this. Okay. And the difficulty is if we just think about rigid bodies in a potential field, we think about those nonlinear systems as being chaotic systems if they are not controlled. You can see on the left-hand side the image of a double pendulum. It is just a mechanical double pendulum, right? And we experience that also for our system. So just elasticities and multi-body systems is a very complex dynamics. And the question arises, how is it that at the end biology succeeds to bring so much order with all these latencies in the neural control and all these limitations? And the tool to study that is, of course, the analogy between muscles and bones on one side and rigid bodies, springs and actuators on the other side. And it turned out that what we are looking at periodic motions, which are far beyond the linear regime, because running just brings you at the limit of your actuation performance. And it turns out that studying this, the ideal tool is geometry, and this brings me to Jean-Paul. And in this particular case, Riemannian geometry, right? Just to start from some very simple facts, looking at a linear oscillator, everything, something which every student in engineering should know, then the orbits in phase space are ellipses. And so assuming you have a conservative system. And if you just look at the projection on configuration space, it's a line where you oscillate back and forth on that line, right? And of course, again, standard engineering, of course you can diagonalize this and then you have imaginary eigenvalues. And then this is also extended to nonlinear systems. And just a simple example, we have two masses, two springs, we have two modes. One is swinging in phase, the other in antiphase. And if you look in configuration space, then again, you will have two lines on which the system will oscillate back and forth, right? And all the other directions, you would have a complex coupled oscillation. So now it was known since the 60s that also some nonlinear systems have those properties. For example, if you have a cubic spring, then you would have something which is not really sinusoidal, but still you will have a line, and if you initialize the system on that line, it will oscillate back and forth on that line. But in the nonlinear case, this is generally not the case, right? But it turns out that you can generalize this idea of saying that in the nonlinear case, you will have a curve which, again, under some conditions for constant energy, if you initialize your system on that curve, it will stay naturally on that curve without any control. So it's a stable orbit. And in order to understand and study that, you need to go from Euclidean geometry to Riemannian geometry. And there was a talk I think in Philippe's presentation, showing that it's about the way you compute distances in Euclidean geometry and in Riemannian geometry. Just, a short introduction for those who are not so familiar to the use. You need to go from planes to smooth manifolds. And of course, the configuration space of a robot, let's see, 2 degrees of freedom. So robot is this square where you then identify the opposed sides. Or if you go, if you would like to have it smoothly, then it's a torus, right? Because you glue the opposing sides together. So it's all about geometry and shortest path on the torus, as we will see. What's the point with the shortest path? Well, in differential geometry, they are called geodesics, right? And if you search for the shortest path in a Euclidean plane, of course, you minimize the distance over different families of, all the families of curves, and then you end up with a straight line. Where if you are on a manifold, for example, on a sphere, of course, there's no straight line, but you could do the same thing, right? Taking all possible paths, minimizing the distance, and you will end up with another shortest path, which on a sphere turns out to be a segment of the great circle. And of course, on manifolds, the shortest path is not a straight line, but what is called a geodesic. And that's why when you look at those maps of airplanes, they fly on geodesic parts and not on straight lines on the Earth, right? And how you do that, basically you integrate the velocity with respect to a special cost function in order to get the length of the curve. So you take the velocity vector, integrate along the curve, and then take the minimum of that, right? And if your cost function is the inertia tensor, then this geodesic minimizes kinetic energy, right? And this proves to be so if your norm of the velocity, is the norm given by the kinetic energy. And this proves to be a useful tool to generalize from linear to nonlinear systems. Why? Well, we all, in robotics directly jump to the Lagrangian formulation of motion or to the Newtonian formulation. But actually, this comes, as we all know, from the principle of least action, which most of the time we do not really consider in detail. What does it say? First, let's take the integral of the Lagrangian, where we ignore potential energy, but just take kinetic energy. Then the principle of least action is just saying that the nature is such that the dynamical system will take a path which minimizes this cost integral, which is the norm of the velocity with respect to the inertia tensor. So basically, the mechanical system is following geodesics with respect to the inertia tensor, right? So trajectories of freely moving multi-body systems are geodesics with respect to the inertia tensor. And basically, this means that you can reduce for constant energy dynamic planning to pure geometric planning. So you can have an analogy between a double pendulum and a point mass moving on a surface of appropriate shape. And basically, you push all the dynamics into geometry, and at the end, you have just Newton's law of a point mass on a surface, right? And well, this is not new, but it might be an interesting news for people used to do motion planning, because they are used to do motion planning with cost functions where the shortest path is not a straight line. Of course, they have different cost functions for us, obstacles and so on, but just imagine of taking your mass sensor as a cost function, and that's how you could plan those motions. Then you will ask what happens if you add potential energy. Actually, this is something which is, I was surprised that in robotics is not so widespread, but in mechanics, you know, Jacobi introduced that, so not the Jacobi matrix, which we all use, but the Jacobi matrix. And you can do the same thing with a new metric tensor, which is just basically potential energy times the mass matrix. So it's E minus the potential energy, which is the kinetic energy. And for historical reasons, there's this too. Meaning that also, you know, if you have the general dynamics equation we know, robot dynamics generally reduces to the motion of a point mass on a high-dimensional manifold if you are in the conservative case. And that's interesting, because this brings you, and I don't know if here at Collège de France we have mathematicians or theoretical physicists, but people doing differential topology and differential algebraic topology and differential geometry, they study geodesics on different types of curves, and there's hundreds of years of mathematical results about this kind of systems. And the first time I came across that is maybe 15, 20 years ago in the book of Arnold, where he shows somewhere just this picture and showing for every two numbers, n and m, you can find a trajectory of the double pendulum which rotates n times around one axis and m times around the other one, right? And just by contracting rubber bands, so instead of shooting what we're doing in optimization, you just contract rubber bands and computer sort this path, right? Which is very interesting. And I asked actually last week for today one of my PhD students to just contract for the double pendulum, you know, this kind of 1, 1, 0, 1, and so on trajectories. This is how they look on the torus, and this is how the dynamics looks like. So indeed, you can find them, and you can need almost no energy to stabilize. So we have seen this double pendulum, which is unstable. You can find, you know, some orbits turning once around one joint and no time around the other one. You can find even more than one, but those mathematical theories guarantee you the existence of at least one solution, which is different from Poincaré map or other shooting approaches. And we remember, you know, this video I've shown at the beginning of being chaotic. Yes, the system can be chaotic, but can be also very, very irregular, actually behave like linear systems. And that's the interesting insight I've got from out of this. And well, these are this kind of circular paths. So just take a rubber band, wrap it around the torus, then let it contract with respect to that matrix, and then you will get an optimal trajectory which needs no energy. Well, but you can have two types of periodic trajectories, of circular type as the one presented, and then this kind of line type. And these are the ones we generalize the eigenmodes of linear systems. And mathematicians called it braking trajectories, because, you know, you move back and forth and brake and stop at one end. And well, let's go very quickly through that. But actually, there's a conjecture which is still not proven by a guy called a mathematician from Heidelberg called Seifert, which says that for every classical conservative mechanical system, which has a equipotential line and equilibrium, you will have at least as many this kind of periodic orbits as degrees of freedom. And he could prove that there exists at least one, but he conjectured that n exists, and I'm in contact still with mathematicians trying to prove that with higher and higher accuracy for our case, right? Okay, now the question is, when is this the case? And I will go just a little bit in detail. So assuming you have a curve, you'd like to ask yourself, can I make this curve to be an invariant manifold for the system without control, just mechanically? Right? And we published a paper with a PhD student of mine and Stefano Stramigioli, showing that the condition for this case is that you make this curve to be a geodesic of the multi-body system, and then the acceleration due to the potential is tangential to this curve. So that's a necessary and sufficient condition, right? If you would like to turn any curve into a stable manifold, right? And a very trivial example is this one, right? Hopping in place, of course, because of the symmetry, you can hop higher and higher, and the system, although coupled and nonlinear, will stay on that manifold. But it turns out that in general, so you take a double pendulum or a full robot, this nonlinear curve so won't be invariant for every energy, but if you take another energy, the curve will deform. And just as an example, take the double pendulum, and this is how those modes look like. So the small cross here are the linearized, so the eigenvectors of the linearized system, and then you increase the amplitude, and then you will always still find oscillations. We have a MATLAB toolbox which gives you those oscillations, but they stand to bend and curve. And this is a representation in 3D, so at small amplitudes you have linear oscillations, and then you increase the energy, you will still have periodic motions, which is very interesting. This is how they look like, for example, for a double pendulum. It very much looks like an arm, with an antiphase oscillation. You remember the two masses, and the in-phase oscillation, and you can imagine some throwing motion or some locomotion based on those eigenmodes. Right? And again, it's natural, and it does not need any control other than stabilization. So, very quickly, I hope that I could give you an overview that initially, we thought that searching for this kind of periodic motions with Poincaré section optimization is about, looking for the needle in the high stack. But now it turns out that there are plenty of needles there in the high stack. There are even some theorems guaranteeing you that there are plenty of needles, right? And there's also some structure. So there are different types of needles. This circular shape periodic orbits, and these break orbits, and what we call strict modes, and so on. So, I thought I will research that for 6 months and then start building robots. Now, after 2 years, I'm still digging into, it's like Alice in Wonderland, where they go in the rabbit hole, and then it gets bigger and bigger, and the whole field of mathematics and fields open up. And I'm just trying to bring this closer to our robotics community. I think it's worthwhile looking into that. Still some results, some practical examples. If you know about those modes, you could first of all try to design your mechanics such that those modes, or what you would like the robot to do, is embedded mechanically into the system. And one of my PhD students, Dominic Lakatos, he compared this two-segment leg with a pantograph structure, and he could show that if you would like to embed a vertical mode, which is just hopping, then the pantograph is much better, because you can, the left one just works with zero masses in the links, while the pantograph works for general parameters. And this might be an explanation why biology, uses this pantograph structure very often in legs. And this is a simulation showing that, if you choose the right distribution of stiffnesses according to the theorem I mentioned, you can have a system which, naturally springs vertically without any control, while with the wrong parameters, it has this chaotic behavior we are used to expect it as engineers. Now we are designing a prototype of a quadruped. Good question after Marco and Boston Dynamics having so fantastic robots while still building robots. But for me, there are templates for studying these motions. So this is a 12 degree of freedom robot. The legs are fixed to the ground, 6 constraints. So you are left over with 6 degrees of freedom. And these are the 6 modes of this elastic quadruped. So it has springs in every joint. And then you can start with your imagination and ask yourself, is it running? Of course, we did not design it for them. It just has equal springs in all the legs. And, but we have a MATLAB toolbox. You feed in the dynamics of the system, and you get out the results. And then you can use that to, interestingly enough, if you detach the legs and excite those modes, the system, starts doing steps. And this is an interesting one, this twisting, shaking. When you detach the legs, it starts basically doing some walking motions naturally, right? Still, there's hybrid dynamics. This theory does not, is not extended to hybrid dynamics to all these cases. So still a lot of work to be done, but I think it's an interesting way. And they are, by the way, very easy to excite. So that's our, prototype just 3 weeks ago set up. And you just take a bang-bang controller, Pontryagin principle, as we heard before, and you can easily, excite those modes. And we are doing first experiments. And again, we have a toolbox. You can take any elastic robot like our humanoid and then trying now to generate some throwing motions based on those modes. And it's going much faster because you are optimizing just in a n-dimensional space. So velocities are irrelevant. It turns out that you just need to optimize in the configuration space. Well, then, just 1 or 2 minutes on the control. We are used, what we have done with Alessandro and many others for years, control, which a lot of control authority, every millisecond, commanding torques to stabilize. This is a mode of a swing. What people are doing are just letting it swing its mode and just injecting at the right time a little bit of energy to compensate for energy losses. So this is the idea, right? Just take the natural dynamics and just give it some kicks at the right time and let it swing, right? And humans are very good at that. I give you a rod in your hand, you will excite a swinging mode, although it's a complex system within seconds, right? Well, I don't have much time to go in the control of that, but using this bang-bang controller along the modes which we pre-computed, it turns out that it's easy to excite, those modes, even in contact dynamics where the robot is hammering against a surface. And even, with some objects which you have never known, these are this kind of gymnastics rods. I don't know if you know them. And then you are asked to excite them in resonance, and the system quite easily identifies those resonance modes. And well, these are steps on the way to a robot which locomotes in those modes. We applied that to different models, and some preliminary results on our hardware. For example, on the white robot over here, we have free locomotion patterns which are, well, they are not perfectly on the theory. I'm still working to have exactly proven that we excite those modes, but close to that, and we had some gates on walking, trotting, and bounding, exploiting the resonance of the system. Okay, and of course, I dream of using that also to explain biological locomotion. These are some motion capture data from animals, which I got from a group in Leipzig. They are beautiful, and they show still how complex, biological motion is. It's hard to get dynamic models of those dogs. That's the difficulty, because we are trying to do some, inverse optimal control and to see if they are really exploiting the modes. And this brings me to the end of my presentation. So I shared this view with Jean-Paul of studying biology, trying to understand basic principles on biomechanics control, but also neuroscience, building robots, and then use those robots to validate those approaches, but also to build better robots. That's the particular thing about us in robotics. Of course, behavior of humans is studied by many disciplines, but what we say is, what I cannot create, I do not understand. So we really want to prove that, the understanding of motion is as good as to allow replicating technologically those approaches. Okay, this is the end of my presentation. Thank you very much.